Someday when you're older, you will learn the joy of multitasking, and Caitlin is joining us again for our last section that we are going to do before our Chapter 5 test. 5.7 is the binomial theorem. All right, the binomial theorem really is just a cool trick that we can use. And before we really get into what that is, let's do a simple example problem for a second. If I had a plus b squared, first of all, remember that means a plus b times a plus b. And if I FOIL that, I get a squared plus 2ab plus b squared. Now let's take a second and let's look at this. Okay, I have a squared here. I don't have a b, but it's really b to the 0 power because anything to the 0 power is just 1. And then this 2ab is the same thing as 2a to the first, b to the first. And where I see a b squared here, you could also put an a to the 0 power there. And then when we do that, we can kind of see a pattern that follows. Each next term, our first part in our binomial, remember binomial means we have two terms, so a plus b is a binomial. The first part of our binomial loses a power, and the second part of our binomial gains a power. Okay, now this is going to be something that's really helpful as we go through today and the binomial theorem. Okay, let's do another one. What if I had a plus b to the 6th power? Okay, that means a plus b times 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 a plus b. All right, let's get started. Okay, just kidding. We're not actually going to do that. We're not actually going to multiply that out. That's where our binomial theorem comes in. Our binomial theorem gives us a much nicer, easier, shorter way of doing that, where we have a lot less room for error than if we actually were to multiply all that out. Here's what the binomial theorem says. When a binomial is expanded, its coefficients follow Pascal's triangle. When a binomial is expanded, its coefficients follow Pascal's triangle. Now, you've probably seen Pascal's triangle before. I don't know if you have learned its name before, but you've probably seen it. And I'll put a copy of Pascal's triangle up here. Now, notice for each row, or I guess in general, our Pascal's triangle, we have ones going diagonally on each side. And then once we get to here, add these together, we get the next number. Add these together, we get our next number. Add your numbers that are side by side and you get the number below it in Pascal's triangle. Okay. Now, I'm not ever going to make you actually come up with Pascal's triangle. I'll give you a diagram, something like this, so you can look off of that. You don't have to memorize or know how to come up with what Pascal's triangle is. Pascal's triangle, by the way, is really cool. There are a lot of really neat applications of it, which I'm not going to get into now, but it's a cool thing to look up. All right, let's look back at this first one that we had expanded. The a squared b to the 0, 2a to the first b to the first, a to the 0, b squared. Keep in mind that I really have the coefficient of 1 here and here. My exponent is 2. My coefficients go 1, 2, 1. Well, let's look at the second row of Pascal's triangle. 1, 2, 1. So my coefficients after I expand a binomial follow the row of Pascal's triangle. That is going to make our life a lot easier when we go to expand a plus b to the 6th power. And we'll do that for our first example here. All right, a couple patterns to follow. First of all, since I know I have the 6th power, that means the coefficients follow the 6th row of Pascal's triangle. And my 6th row, that's the bottom here, 1, 6, 15, 20, 15, 6, 1. So I'm going to have a lot of terms when I expand this. But these are my coefficients. I'll write that down here. My 6th row is going to go 1, 6, 15, 20, 15, 6, 1. All right, so we're going to use these coefficients and also the pattern that we noticed up here where each term, our first part loses a power and our second part gains a power. We're going to use those patterns to expand a plus b to the 6th. So my first term, my first coefficient is going to be 1. And I'd have a to the 6th power, b to the 0. Now I like to write the b to the 0 term in right away, and then I'll get rid of it later when I simplify further, just because it helps me keep track a little bit more of everything else. And then my next term, I'd have 6 as my coefficient. A is going to lose a power, B gains a power. So we lost a power going from 6 to 5, we gained a power going from 0 to 1. My next term coefficient is 15. A is going to lose a power and become the 4th. B gains a power and becomes the 2nd power. And then we keep going. We'd have 20, a to the 3rd, b to the 3rd, 15, a to the 2nd, b to the 4th, 6, a to the 1st, b to the 5th. And let's see if I can slide my paper over here. One a to the 0, b to the 6th. Now something else to notice, the total number, if you add your exponents together, should be 6 each time. And that's our exponent that we're raising our binomial to. After we do that, we can just simplify a little bit more. We don't really need the 1 as the coefficient. We don't really need the b to the 0 power. We have a to the 6th. And here I don't really need the first power. a to the 4th b squared, 20a cubed b cubed. Okay, and then this bottom row would be our final answer. Now we would have the same thing here if we actually took a plus b times 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 a plus b. But I don't know about you, I'd much rather do this than actually have to multiply all of that out. So easy to make mistakes along the way. But that's our binomial theorem.